So we're about to make a transition from the two halves of Calculus 3. We've just finished the Hessian, the second derivative test. We found the extreme values of a function on the interior and the exterior on the boundary of the region. And so we've essentially, with those kinds of problems, finished the derivative section of Calculus 3. We're now moving on to the integral part of Calculus 3, and we want to focus on the integrals over simple regions called rectangles. And then we'll motivate double integrals using the Riemann sum in this video. So essentially what we're trying to do is to, in this video, just provide excuse me, a motivation for double integrals, okay? And it would help if we could just kind of recall what happened in Calculus 1. In Calculus 1, we know that we're used to, y is equal to some function of x. And maybe that function of x is a nice simple function like a straight line x plus 1. Okay. And then we also had an interval. You had that function defined on a certain interval, a to b, and maybe we could say that that's maybe 0 to 4 in this case. And then once you had a function in an interval, you could then create a graph of that function, 1. You would create a straight line, x plus 1, and then on the interval 0 to 4, right, the function would be up here at 5. So here is our function, and we then, in Calculus 1, you ask the question, we introduce the definite integral notation, the integral from a to b of f of x dx. And this notation was a very loaded notation, because what it actually meant, this notation means to do a Riemann sum with n going to infinity number of rectangles. So we might want to recall Riemann sum in the Calc 1 sense, right? So there was the actual meaning of this notation and how and how what that notation meant. And then in Calculus 1, you started to develop shortcuts for computing of that integral, right? And for computing the integral, there turned out to be a very important and key result, which was called the fundamental theorem of calculus. And the fundamental theorem of calculus says that if you can compute this definite integral using a Riemann sum, that it also happens to be equal to the antiderivative of the function that you're finding the integral of, and then evaluated at b to a. So this would be the antiderivative at b minus the antiderivative at a. So what we had was a key result for computing the integral using the fundamental theorem of calculus. And so one could easily get a number here, right? But then the interpretation of that number, what was important about it, came from actually the meaning of the notation in Riemann sum. And we knew from Riemann sum that if you maybe tried to split this problem up into 4 rectangles, we knew that when we were doing a Riemann sum that we were adding up the areas of rectangles, perhaps. Right? So we're adding these areas up. And so that, because of that background, we knew that this number, as n went to infinity, n going to infinity rectangles, that the definite integral could be interpreted as an area under the function f of x, but on the interval I going from a to b. Okay. So that was the motivation and how Calc 1 probably happened. Okay, so in this case, I just want to finish just reminding us a little bit about Riemann sum, and then we can remind ourselves about the fundamental theorem of calculus for Calc 1. and then we'll extend that to Calculus 3. So that's kind of the overview of this section. So this is motivation part 1. Motivation part 2, I'll go ahead and carry out all the steps for Calc 1 that I just laid out, and then Calc 3 will occur in later videos.